In this screencast, we are going to talk about amide formation, how to name amides, the properties of amides, and some reactions that amides will undergo. So amines can react with acid chlorides or acid anhydrides to form amides. The characteristic functional group of amides is a carbonyl attached to a nitrogen. There's a single bond linking the carbonyl carbon here to the nitrogen atom, and that's called an amide linkage. When we look at these, amides may be thought of as containing an ammonia or an amine portion here, and then a portion derived from a carboxylic acid here. However, we've already looked at a reaction of amine with a carboxylic acid, and that normally produces a salt and not an amide. So for this reason, the preparation of amides requires a more reactive acid chloride or acid anhydride, and we've seen those be more reactive in previous screencasts. So when we take an acid chloride and we react it with an amine, this is how we form an amide. We also form hydrochloric acid here as the side product. Now, both a primary and a secondary amine can react with an acid chloride to form an amide. Tertiary amines don't, and the reason is because they lack a hydrogen on the nitrogen. So primary amines, let's say it even different, primary and secondary amines can form amides, but tertiary amines cannot, because there is no hydrogen on the nitrogen. So I want us to look at some examples of this. So let's look at a primary amine. In a primary amine, we're going to notice that there are two hydrogens on that nitrogen, and it will undergo a reaction. And when we predict the products on this reaction, the amine switches places with the chloride. So look here. Here is the amine right here. Okay, and we can see now how that has been attached right here. And then we also get hydrochloric acid. If we do the same reaction, but instead look at a secondary amine, okay, then what we can do is we can say, okay, let's look at everything except the hydrogen on the amine. So all of this and all of that is going to take the place of the chloride right here. So when we go to draw that product, we take the C double bond O and remove the chloride, and now we have the amide there. And again, tertiary would give us no reaction. Now, so we've looked at acid chlorides and how they can form amides. The other thing that can form amides are acid anhydrides. And this is an example of a reaction of an acid anhydride. It's a general reaction, so I wanted you to also see a like a specific reaction. So we've got an amine there, and we've got an acid anhydride. I want to remind you that an acid anhydride can be identified because it has a carbonyl group, an oxygen, and then another carbonyl group. So there's an oxygen between those carbonyl groups. When we react with an amine, and the amine that I'm going to use is ammonia, what we see is that basically we can split this right here, and this part here, right, is going to react with this part here. And so that will come together to form the CH3, C double bond O, and then the NH2. And so we can see that all through here. Then the other part will form a carboxylic acid. So you'll also get CH3, C double bond O, OH, where this and this react to give you this. And so that's how we would go through and predict those products. Now, similar to esters, amides can form polymers. When they form polymers, these are called polyamides. And so what happens here is you have a reaction of a diacid chloride. Okay. And so when we talk about a diacid chloride, this is an example of it. We have two of those carbonyl groups and then a Cl there and then a Cl here. So this is that acid part they're talking about. So two acyl chlorides that are attached. A dippyl chloride is a really good example of this, and it reacts with a diamine. So an amine with a molecule with two amine groups, and that produces a polyamide. And so here's a polyamide. These are held together with amide linkages. A really good example of this is nylon. And so this is the way that we produce nylon. It's a really interesting process. These two don't mix, so nylon's formed at the interface where they both come in contact with each other. About 3 billion pounds of nylon and related polyamides are produced annually. A lot of the nylon fiber is used in home furnishings like carpet, or textile fibers in clothings, or tire cord. Minor uses include like fasteners or ropes or parachutes, paintbrushes, and electrical parts. Now in medicine, nylon's used in specialized tubing. You can have nylon sutures, and then Kevlar, which is another polyamide, is used for protective vests. So those are bulletproof vests. And so those are also quite important. Now, silk and wool are natural polyamides that we classify as proteins. And so for now, what I really want to emphasize here is that the repeating units and the amide linkages are characteristics of proteins. So this would be an example of what we would call a protein backbone. And it's got these repeating amide linkages. So again, we are going to study this more in chapter 19. Now, let's talk about how to name amides. So when we name amides, we are going to use the carboxylic acid name. We're going to drop the ic ending or the oic ending and change it to amide. If there's an alkyl group, then we are going to give it the name, and it precedes the name of the amide. And then we use a capital N to tell if there's an alkyl group that's bonded to a nitrogen. So let's go through and let's name this amide. Okay, so when we look at this amide and we're trying to figure out what to name it, we need to think back and basically replace the NH2 with an OH. So we would come here and we would say, look, if we replace that NH2 with an OH, that it would give us this particular carboxylic acid, which we would name as methanoic acid. So to give this the amide name, we would say, hey, look, this is methane, but now we are going to drop that oic acid part, this part right here, and instead just say, look, it's methanamide. We do the same thing with the common names. So the common name for this is formic acid. And so we would call this formamide, right? When we talk about, let's look at benzoic acid. So when we think about the amide that's similar to benzoic acid, it would look like this. And so this would be benzoic acid. And we would remove the oic acid part and we would just call it benzamide. And so these are some ways that we can name amides. Now, let's look at another example. So let's look at this guy here. So when we look at this guy here, right, we have it's helpful to identify where your carbonyl is and look at the amine here. And then what you do is you name everything that's kind of connected to that carbonyl using the name of the carboxylic acid right there. So, for example, we would say, okay, we know this base name is still methanamide, right? And now, but we need to also name this guy here. When we do that, that's where we use that capital N. And so we would call this N-methyl methanamide. Sometimes you can have two groups that are off the nitrogen. And so I want us to look at this molecule. And so again, it's really helpful to use colors to divide this up. Identify where your carbonyl is, and then go to your nitrogen and stop, and then look here. This part here is derived from a carboxylic acid, and so that carboxylic acid would be CH3 C double bond O OH. And so if we were to name that, we'd name it ethanoic acid. And so I'm going to drop that oic acid there, and I am going to name this as ethanamide. But I also now need to come in and name these two groups here. Now there are two groups, and so because there's two groups, you put the N twice. And so it would be NN dimethyl ethanamide. And so that's how we would name that particular amide. Now, let's look at some physical properties. And the first physical property I'm going to talk about involves formamide, which is this guy right here. So I wanted to definitely put that out before we got there. Formamide is the only unsubstituted amide that's a liquid at room temperature. And I'm going to abbreviate room temperature as RT. All other unsubstituted amides are solids at room temperature. Now, one of the things to notice here with these properties is there's pretty complex hydrogen bonding between these amides, and that causes them to have high melting points. So we have hydrogen bonding between the unsubstituted amides. And when I say unsubstituted amides, I just mean that on that nitrogen there are two hydrogens, right? So there's no other R groups. And it causes them to have high melting points. And I want to show you an unsubstituted amide. What we're talking about here is you've got an amide, and when it's unsubstituted, it means that there are two hydrogens here. There are not any CH3 groups. Now, when you substitute a alkyl or aromatic group for hydrogen atoms, that reduces the number of intermolecular hydrogen bonds that can form, and it causes the melting point to decrease. So we have unsubstituted amides here, and then we have disubstituted amides here, and you can see in an unsubstituted amide there's a hydrogen here and a hydrogen here, and both of these can bond with water, hydrogen bond with water, and then this carbonyl can also hydrogen bond with water. Well, if one of those hydrogens are replaced with, or both of them are replaced with a R group or a CH3, now this can only form two hydrogen bonds. So we end up with a lower melting point. So the substitution of an R group for a hydrogen on the nitrogen reduces hydrogen bonding, and then what that means is the melting point will decrease because of that reduced hydrogen bonding. So that means that disubstituted amides often have lower melting and boiling points than monosubstituted or unsubstituted amides. And so we're going to see in chapter 19 that hydrogen bonding between amide groups is really important in maintaining the shape of protein molecules. So this will come back. Now, amides are rather water soluble, especially those containing fewer than 6 carbon atoms. The solubility results from the ability of the amides to form those hydrogen bonds. So, right, amides are, quite water soluble, right? Especially those that have fewer than 6 carbon atoms per amide. Okay. Now, let's look at some amide reactions as well. So amines were basic, and so we might want to jump up and say, oh, I bet amides are basic too. Well, it turns out that amides are not really acidic or basic. So these are neither acidic or basic. The carbonyl group bonded to the nitrogen has really destroyed the basicity of the amine, and the nitrogen of the amine has replaced the acidic portion of the carboxylic acid, and so that's why we end up with no really acidic or basic sites. Now, the most important reaction of amides is hydrolysis, and this reaction corresponds to the reversal of amide formation. And so what happens is we add water and the amide bond is cleaved and we form a carboxylic acid or an amine. There are two ways to do this. You can either add acid or you can add a base with heat. I want to let you know that another sign for heat is a delta there. So delta also stands for heat. So let's look at some really specific examples here. So when we're doing an example, if we have, for example, CH3, C double bond O, N, CH3H, and we react it with water and HCl and heat it, what we find is if we were to draw a line right here, this is how we would cut this molecule apart. With this part coming over here to form the carboxylic acid. And then this part here forms an amine salt. And then this is the counter ion that goes with that amine salt. And so that's what happens when we react it with an acid. When we go through and react it with a base, we are going to heat it again. And again, you need to come here and kind of split this. And what's going to happen is we're going to end up with a CH3, C double bond O here, and then you're going to have an O minus. Now, that O minus is going to complex with this sodium right here, and the sodium is going to be its counter ion. Then, for this part here, that gives you your amine, which is CH3NH2. So these are the two kind of big reactions that amides undergo. Now, amide hydrolysis is a very important reaction in biochemistry. It's really central to the digestion of proteins and the breakdown of proteins within cells. However, most of this amide hydrolysis in the body is catalyzed by enzymes rather than by strong acids and bases. So one of the things that we need to kind of think about when we talk about amides is that many of amides play really important roles in medicine. And so you can see these different compounds here which have amide functional groups. And so if we were to go through and we were to highlight, this would be an example of an amide functional group. There's an amide functional group here and here. Here would be an example of an amide functional group. Here is an example of an amide functional group. Here is an example of one. If we look at those functional groups, you can see here how these amides play a part in many of our medicines. And so these are the generic name and then the trade name, and then this is what they're used for. Ampicillin, which is known by its trade name polycillin, is an antibiotic, and so that's one that ampicillin is one that I've personally come in contact with. Valium has an amide. It's used as a tranquilizer. There's treatments of insomnia as well as intravenous anesthesia as well. So we see these pop up in biochemistry and in medicine quite frequently. Well, this for us ends our section on organic chemistry. And so we've talked through all the functional groups. And now in the next screencast, we're really going to change gears and we are going to focus on biochemistry and biomolecules. As always, if you have any questions, please feel free to pop by my office.